Maxim, I don't hear you.
Andrei, that was because I muted my microphone, so you don't hear any echo from me.
Okay.
Now I have a...
Okay. You may wonder what is the relation between this woman and the topic I'm going to talk about.
Andrei, we couldn't see you. Could you adjust your camera a tiny little bit so that we could see
You should see not me. You should see the screen.
Okay, fine.
Okay, you can see me in the small window, but you see this woman, and the question would be how this woman is related to the topic I'm discussing. And her name is Denise Billman, and she is a figure skater. And I want to show you some video. That is kind of relevant to the topic I'm going to discuss. Namely, it is relevant to the topic of inertia. So I'll show you this video again. So please do not be surprised that you will get a video. So please do not pay too much attention to pretty women. I am interested in physics. Just see what they are doing. Okay, so what they were doing? They were clearly, strongly increasing the speed of their rotation. So it was something that surprised Newton, as I explained to you before. So first, these women had slow rotation. And then they did something. And rotation became fast. So what they were doing? And it will be one of the topics that I'm going to discuss today. Actually, as you saw there, before they put their legs like this and then rotate. Then they were putting their leg upward. And speed of rotation increased. So what kind of inertia is this? It means actually that it is not the angular speed that is constant. There is something else that is constant. So we know what actually is constant. And what is constant is called angular momentum. So what is the angular momentum? It's not the angular speed. To understand the origin of the angular momentum, I want to show you another person. So today you will see a lot of people. You may see her like this. This person was, this great woman was Emmy Noether. Who discovered the famous theorem about conserved quantity in physics. She discovered that conserved quantities in physics are in one-to-one correspondence with symmetry. And let us see what kind of symmetries do we have. First, we study with one-dimensional motion. And if we have one-dimensional motion, the symmetries are constant shifts, then we study motion in dimension 2. And when we study motion in dimension 2, then this is our space. Then together with shifts, we also have rotation. And then there are conserved quantity corresponding to shifts and to rotation. So up to now, I told you only one fundamental law. Mi dri over dt square was minus derivative with respect to Ri of the total potential. And I call that DNM, Democrit-Newton mechanics. So let me consider the first symmetry. Suppose that when all Ri's simultaneously are shifted by C, then U of R1 plus C, etc. Rn plus C equals to U of R1 Rn. And of course, second derivative is not changing. Is not changing. So let me illustrate this symmetry here. Later on, I will give you a complete derivation, but because this is not the final formulation of physics, even of mechanics. So I should stop drawing a miniature, and I could show you the formulas. So the main statement is that the following object is conserved. Mi sum I going from 1 to n, mi dri over dt, called momentum. So how to show it? Let me take derivative of the left-hand side. Here I go to the right-hand side. And I write exactly what I had. Substitute main equation. Minus and what do I have here? I have here d over d Ri of u, R1, Rn. But now look, this is nothing but the change of potential when I'm making the symmetry. And I assume that potential is invariant. That's why it is 0. So this is actually P, variation of potential, corresponding to C. And that's why it is 0. Okay. So, so far, so good. Now, how can we explore? Now let me consider dimension of space to be 2. And let me demand the following. I'd like to demand that the potential is invariant under rotation. And rotations are given by a vector epsilon. So I'll write it like this. U of R1 plus R1 for small omegas, etc. Rn plus omega Rn equal to U for small omegas. Okay, it would work in dimension 2, it would work in dimension 3. Oh, see, in order not to confuse it, let me consider d equals 3, but motion would be 2-dimensional. Okay, but so that's what I'm studying. And I hope that you know that this vector product of vectors corresponds to rotation. Now, I would like to have a trick similar to that trick. It turns out that I should consider the following conserved quantity. It is called rotational momentum. It is a sum of mi, I going from 1 to n, times rotational momentum of each particle. And this is R times Ri times dRi over dt. Now let me do similar things. Let me take the total time derivative of momentum. You see, my computations are very simple, and I will do them explicitly. So here I will have two terms. First term would be the vector product of velocity. This is called velocity on itself. And this is 0. Plus mi dr plus mi, and here I'll have ri times d2 ri over dt squared. And now, what can I see? I will plug in my DNM formula. And I will get sum from I going from 1 to n. All this thing together go to Ri times this. Du over dRi. But now note that this is exactly the change of u when I make a rotation. Actually, when I'm making a rotation, I take derivative with respect to r. And then I take a vector multiplication by omega. So this is 0 due to rotational invariance. Okay. Now, finally, how does it apply to this figure skater? Let me see what is actually preserved. If I rotate, each part of this skater, its velocity, goes like omega times Ri. And this is called angular speed. Speed of the angle. So I assume that this is known. Then I may put it here and see, and I will see very important formula. That momentum, and it is something that is conserved, is something like this. Now assume, for simplicity, that I have a vertical axis z, and all rotations happens here in the plane, as in the case of figure skater. Then, so omega is parallel to z. Arms are perpendicular to z. Actually, other arms just do not matter. In this case, I can strongly simplify this. Because it would go into sum I going from 1 to n. Omega would become a scalar. And here I'll get this. So this is, and I can take omega out because I have a collective motion. So I see that what is preserving, not omega is constant. Rather, what is constant is omega times this object. It is called moment of inertia. It depends on R. So what happens when skater is going from this to this? So let me consider projection of the skater to the plane. So here, the skater was like this. And here the skater was like this. So moment of inertia in this process goes down. You see, because it's proportional to the square of the distance between pieces. So that's why omega goes up. Okay. You may think that it is just a particular phenomenon that I study. The topic of my today's lecture would be not to show you some phenomena. the topic of my lecture would be to show how geometry appears when you try to study mechanical systems. So here in physics, you study skaters, but then it happens that you are coming to necessity to construct new mathematics. And if you think what kind of mathematics appears here, you would see that there will be two pieces of geometry that appear. One piece of geometry would be so-called differential geometry. The second piece would be algebraic geometry. To find both of these geometries coming from physics, you should just look at particular physical problems as a theorist, okay? You start trying to understand phenomena, and you immediately construct geometry that was fully developed in the 19th and then in the 20th century. Later on, if you include here electromagnetism, elementary particle physics, it will still be understandable in terms of this geometry. So that's how it goes. You start with mechanics, you got new math that was not known before, and this math plays back, okay, in the 20th century physics. However, my main message is that in order to construct this math, the only thing you need to do is just to think about mechanics. Also, mechanics give you some intuition about this mathematics. And then this mathematics gives you the language to describe physics. So, let me show you more experiments in physics. Once again, I will not do experiments for you, but I will enjoy the modern technology. And in this modern technology, I will just use experiments done by other people. By the way, Maxim, could you tell me, was it possible to see the video? Maxim?
Yeah, I'm here. Which video, Andrei?
With the skating.
Yes, I was able to see it.
Okay, good. Then I will show you more videos. Okay? You see, instead of making experiments myself, I can do it this way. So I will share a screen again. So please don't be surprised that you would see videos. So do you see? Okay. So let me check what I'm showing you. I should show you this video. And here we see the experiment with the gyroscope. So gyroscope was balanced. So now it falls. So what would happen if you spin the gyroscope? Okay, so I increase the speed, not the speed of gyroscope. So he runs the gyroscope, the man. And now interesting thing happened. He can take out this piece, but gyroscope is not falling. It looks as if the mass of the gyroscope went down. Even like this, gyroscope is not falling. Only now it could fall. So the question is, how could it be? But when you stop the gyroscope, and he would do it, so now it goes like this. Then the balance line would be the black line, not the red line. So previously the balance line was the black line. So now he will stop it. Wait for a second for him to stop it. Ah, it's not in balance anymore. Now it's in balance. Anti-gravity. Come on. So another experiment with the gyroscope. He is just fixing the gyroscope this way. And then the gyroscope becomes rotating by himself, doing this crazy and strange motion. So how could it happen? Okay. I am not going to explain to you each particular experiment. I just want you to see that there is an interesting issue. And this interesting issue is mechanics in 3D is even more interesting than in 2D. A lot of phenomena. So, how to describe it? And what is the difference between the gyroscope and the simple DNM system that I wrote to you? DNM system had a lot, actually 3 and variables. That was R1X, R1Y, R1Z, etc. up to RNZ. And we studied just differential equation. But N is enormous, like billions. And we cannot study this in all detail and see some phenomena. In order to see some phenomena, we need the concept of the solid body. So what solid body means, actually? It means that distances between particles are fixed. Why are they fixed? It's because this potential contains terms like lambda, Ri minus Rj squared. And lambda is like going to infinity. So it allows us to simplify this enormous system. So before I will do it, I will show you how algebraic. Sorry?
Would you please, the camera, we cannot see what you write on your left.
You mean here?
Oh, yeah, we cannot see what you write there.
Oh, I'm sorry. Thank you.
Yeah, thank you.
So these things are called constraints. So what is the proper mathematical way to write it? You have a function of x1, xm. Okay, no, you have variables, and constraints are functions. F of x1, xm, that you put to 0. So what you study would be a constraint configuration space. And this constraint configuration space is the space of solutions to all these equations. So if you know a bit of algebraic geometry, you see that these equations are quadratic polynomials in coordinates. So what we are doing so-called intersections of quadrics. So this is what we want to study. And proper way to study the intersection of quadrics is, of course, algebraic geometry. Because, and I'll come to it later on, not now.
Andrei, would you please write down the equations once again, the quadratic equation, so that I could see it, that the squares of distances, that the squares of distances are constant, right?
Exactly.
Thank you. Yeah. Thank you. Thanks.
I call it Vij square. These are parameters.
Okay, thanks.
So one way to have a look at it is that we are solving quadratic equations. So it is easy to solve linear equations. However, to solve quadratic equations is a bit more tricky thing. Okay? Now, the proper way to do this is to do the following. So this is the space of solution. Let me call it Y. And then there is an interesting thing called algebra geometric correspondence. And in algebra geometric correspondence, you do the following. You are going from the space Y to the algebra. Algebra of functions. On Y. And the corresponding algebra of functions is just the algebra of polynomials divided by ideal generated by constraints. And this correspondence is so-called contravariant. Namely, if you add more equations, then you have a space Y tilde. So you have more equations. However, the algebra, so let me call this AY. The algebra go in the opposite way. So actually, maybe, okay, this is called, maybe it's better to speak not about the algebra, it's better to speak about this I. This is called ideal generated by Fi. So what ideal is? What ideal is? Ideal is a space of PA of X times Fa of X. The space of this combination. Okay, so instead of talking about algebras, it's better to talk about ideals. And it is interesting that you may say that Y corresponds to the ideal Y. And when you add more constraints, the ideal becomes bigger. Then you have this correspondence. Here arrow inclusion goes this way. Here it goes this way. And this contravariant correspondence is called algebra geometric function. So you see how algebraic geometry appears. So what we were doing, we were just talking about solid body. But if you talk about solid body with taste, okay, you are not just doing these gyroscope experiments. You can do many of these experiments. You would immediately see that you have to study subspaces described in this particular way. So here, I haven't gave you the definition of what space is and what subspace is. So I assumed that that the configuration of unconstrained system is given by R1, Rn. And in the 19th century, it was understood that this collection of vectors could be considered as a vector in the space R3n. So it is a huge vector space. Now, once again, I'm having here constraints. And here we have subspace. And this subspace is similar to spaces that we used to have. So what kind of subspaces we used to have in geometry? In ordinary geometry, we used to have R3. So we can see it. And there are subspaces like the plane. So plane is simple. It is given by this equation. We have also a line that is an intersection of two planes. Not that interesting. However, in ordinary geometry, we have objects that are not linear, okay? Quadric. And the first quadric happens already in R2. It is a circle. And we can draw it. Now, what happens in R3? So this was studied from the long time ago. So simplest case was this. Sorry, not 0, r squared. And we can draw it and imagine it. Moreover, we will not need it immediately right now, but we can also study something like x1 squared plus x2 squared minus x3 squared equals r squared. So we can also draw it. So it's called hyperboloid. So these are quadrics. And we may also intersect quadrics with quadrics and get some kind of curve. Now, note that in mechanics, we should study intersection of quadrics in R3n in the space of the very high dimensionality. So we need to find some mathematics that would allow us to work with this space. Okay? And I told you that there are actually two types of mathematics. One was algebraic geometry that I just outlined in terms of this algebraic geometry factor. Then instead of studying geometrical problem, we will study algebraic problem. We will talk about ideals. We will talk about algebra given by generators and relations. And second is called differential geometry. And in differential geometry, we would say that, look, consider a sphere. Locally, it's like a disk. And there is a way to speak about sphere in terms of its local data.
Sorry, Professor, could you
Yes.
move the camera a bit up?
Thank you.
Thank you, thank you.
And also, we should increase our imagination. Because here it is easy to understand S2. It is easy to understand. But we need to imagine more complicated spaces. In particular, in increasing imagination, we need to understand sphere in the n-dimensional space. x1 square plus xn plus 1 square equals to r squared. So, how can we increase our imagination? I will tell you a general trick how to increase imagination. It is try to do it step by step. First, try to understand what S2 is, starting from S1. So everybody understand what S1 is. It's a circle. S2 is now consider x3 as a parameter. Then for given x3, we have the following equation. It means that if x3 is less than minus r, we have no solution. When x3 equals to minus r, we have a point. And then when x3 is bigger than minus r, a circle appears. And when x3 equals to 0, it is maximum. Then the circle goes down. And then everything disappears. So this is the way to see S2 in terms of, to imagine S2 in terms of family of S1. So I explained it to you because you may also consider this third direction as a time. You start with nothing, then a point appears. It grows to a circle, then it shrinks back to a point. And this is S2. Now here, we will go and imagine this. Now, how to imagine three-dimensional sphere? We cannot put three-dimensional sphere inside our space, okay? It is something in the four-dimensional space. And you may think that it is impossible to imagine it. However, you can improve your imagination like this. Here we had a simple example, a toy example, how to imagine higher dimensional sphere in terms of lower dimensional sphere. Let us apply it here. And if we apply it here, we would say that S3 is the following. First, you have a point. Then you have small S2 that grows. Then you have big S2. Then you have small S2. And then it comes back to the point. In this example that I gave you, I showed you the way how to imagine. You see, without imagination, you cannot do anything in mathematics. Without imagination, you cannot do anything in physics. In mathematics, you have to imagine spaces. It's called geometrical view. In theoretical physics, you have to imagine theories. And as you see, theories are even more interesting than spaces. Okay, I think that I would like to make 7 minutes break. And then you will ask questions. We'll go on. Maybe you have an immediate question right now.
I have a question. Can you hear me?
Yes, sure, I can hear you.
I can see from the lecture that a given symmetry of the potential functional can induce a conservation law. So my question is it true that conversely, any conservation law is induced by certain symmetry of the functional?
Absolutely. But in order to get the deeper understanding, we have to go 2 languages up. First language would be so-called Lagrangian language of classical physics, when it is a mathematical theorem. But then we will go 1 level up, go to so-called Hamiltonian presentation of Lagrangian language. And then it would be 6 symbol statement. So this statement that we think is deep in the proper language is AB equals, that from AB equals to 0, it follows that BA equals to 0. You see, while you are developing language, statements become more and more transparent. And this is a reason to develop a language. Okay? What you see is a coincidence when you do not know language.
Yeah,
would
thank you.
become-
That's very inspiring.
So follow my course and we will come to this.
Yeah, I look forward to that.
Okay. Still, I have to make breaks. Now I'll make a 9 minutes break. Okay? And after the break, I'll first answer questions and then I will continue. Okay? Okay, so let me continue. So here you may see that I have a cat. Okay. Cat is easy to operate, very easy to operate, right? Maxim, do you see the cat?
Yes, absolutely. And I'm afraid I know which experiment you are trying to do. I'm afraid so.
No, please don't afraid. He would not be harmed. So actually, in this course, I am going to teach you some wisdom. And wisdom is to understand deep things in simple examples. So imagine that you have to deal with a tiger. Like with gyroscope. So gyroscope, or even more complicated things, or nature around us, is kind of a tiger. You could be surprised, it could be dangerous. The wisdom is to understand the tiger is just a particular piece in the family of cats. And then, in order to understand something about a tiger that you really need, you do something with the cat. You could not do it with the tiger, but you can do it with the cat. So this is a scheme. And then you have just ordinary cat. So in order to study tiger, you study cat, and then you generalize. Okay? It is a trick of wisdom. In science that is called mathematical physics, tiger is replaced by reality. So instead of reality, in mathematical physics, people consider reality as belonging to the family of possible worlds. And then cat is just the model world. Easy to operate. So that's why all examples that I will show you happen in model worlds. Okay? And then I'll say, okay, I understand what happens in model world. Then I understand how it happens in reality. So this is mathematical physics. And when you study model worlds, you see a lot of mathematics coming up. So mathematics for me is an operational tool in the model world. And there is an art of making Simple model. So it is an art, it's not a science. So I would not give you instructions how to do it. But from our course, you would see how I do it in many examples, and you would be able to do it yourself. You see, if properly understood, all questions could go to
I
this.
was so scared of, you spoke of the angular momentum. Yes, so you spoke of the angular momentum today. There is something called cat-fallen angular momentum paradox, which is that if you lift your cat with its paws up, its feet up, and let it go, and when it falls, you will find that it lands with its feet down, and it contradicts the conservation of the angular momentum. So I was
doesn't
afraid that you are,
It doesn't contradict the contradiction of the angular momentum. Because
Yes,
suppose you
but-
have a cat.
so I was afraid that you are going to reproduce this experiment in
No,
front
no.
of us.
No, you see, once again, I am a theorist, okay? I'm not reproducing experiments. It's not my job. My job is not reproducing experiments. So there are people who do it in much better way. My job is just to explain experiments. And I am explaining experiments in a very special way. Instead of explaining particular experiments, I'm showing you the way where to go and what to do in order to be able to explain all experiments in the field. Okay? I am not a person who explains things. I am explaining, so what I am explaining, structure of science. I am explaining languages that you have to do in order to solve your particular problem. So if you are interested, say, in rotation, in the motion of the solid body, like a person whom I showed, he was very surprised with it, doing this experiment, that experiment. Or if you're trying to make perpetuum mobile, or things like this, you should better understand the science. And for me, the best understanding of science is to find the proper language. But in order to find the proper language, you need to take your piece of science in the higher context and find the model and solve the model. And when you solve the model, you would be able to understand what happens in the very particular case. And I say that it is the only way, from my point of view, how science goes. Okay? So in order to solve a problem, you need to put it in the proper context, you generalize, and only then you are solving your particular problem together with many other problems. Okay? So what I told you is that in order to understand motion of a solid body and I say, and many, and a lot more, you should do the following. First, you should develop geometry. In two contexts. First context is in the way of algebraic geometry, where there is a deep statement. It's about contravariant. I'll repeat it because some important things has to be repeated. Function between spaces and ideals. So to get some wisdom, you should understand this contravariant function. And when you will understand this contravariant function, then you could apply it. In particular, when you say Ri minus Rj squared equals Dij, these are particular quadrics. So you can see rotational symmetry. R is, okay, another omega, is rotated. It is obviously a symmetry. And it is obviously a symmetry and that's how you get this angular momentum. And that's why you have these quadrics. And second thing, it is differential geometry. Because, okay, system is a point in some space. In R3M, called configuration space. But we need to understand its evolution. How this point is moving. So once again, I will follow my cat example. So the simplest example of this configuration space, the simplest, would be the circle and the sphere. So this is the simplest example. Let this be configuration space. It's such a system. This point is fixed. This point is moving. Okay? Here we don't have translational invariance. Here we also only have rotational invariance. So configuration space is a circle. So we need to understand what is the meaning of a speed. So we think we understand what the speed is. So speed of a particle here is a vector. We thought we know it in R3M. However, it should be such a vector that preserves constraints. And this is the notion of the tangent vector. So speed is a tangent vector to configuration space. So if you keep it in mind, it would open you the world of differential geometry. So algebraic geometry is to understand the space, and differential geometry is to consider motion on this space. And once again, we are coming to the issue of inertia. So what is the moment, man? Sorry, what is the momentum? In d equals to 3. So if we study what is the momentum in d equals to 3, we would understand a lot. So it is a conserved quantity. So what have we observed? We have observed the following, that you take a symmetry, and also you take velocity, and from symmetry, velocity, and also you have some data. It was called inertia tensor. And from this, you consider this rotational momentum. So we can study it as a particular example. But the deep question is how to generalize it. So you may think that generalization of this concept has no application. And if you'll do this, I'll tell you that you'll be completely wrong. Because generalization of this concept led to so-called gauge theory. That is the heart of our understanding of the universe. Okay? So you start with a simple question. You just try to think a bit deeper, okay? Not on the level of just writing down formulas, but on the level of meaning, trying to understand what it is. And you are coming to the very deep things. Okay? So here we are coming to the question, what's the symmetry? So heuristically, we know the following. A, symmetry preserves something. Second, okay, symmetry preserves something. In the case of rotations, in baby example, so symmetry preserves length. B, they could be composed. And composition can be inverted. And this actually means that they form a group. Now we are coming to the point C. These symmetries could be discrete and continuous if they are continuous. Like rotation on angle phi. They form the space themselves. So let us think about rotation. You can rotate a system on an angle phi. However, if you rotate a system on the angle phi equals to 2 pi, it is identical. That's why rotational symmetry in D equals 2 form a S1. And S1 is just an interval where you identify 2 points. So then the proper question is, what is going on in D equals to 3? I don't want to say that, you see, the answer is not that formulas are such and such. It's not a good answer. First of all, we need to know how many rotational symmetry do we have? And second, what is the space of this symmetry? So the answer is quite surprising. And we will discuss it later on. But you see, in order to start some computations, you see, you need to know why. You have to spend your time to do this computation and why you want to understand it. It's because rotational symmetries in D equals 3 actually form a very interesting symmetry. S3 over Z2. So I already told you that it is important to imagine S3. I gave you one way to imagine it. There is another way to imagine it. How to imagine Sn second way. So algebraically, it's of course a space of solutions to this equation. However, they could be imagined in the following way. Let xn plus 1 be positive. Once again, consider it as a parameter, and then solve equation. So what do you have? You will have a sphere you will have a sphere SSN filled in. It is called a disk. So disk is a space of solution to equation x1 squared plus xn squared is less or equal to r squared. It's called a disk. So for n equals to 1, d, so it's called, so sphere is called dn, but this is called dn plus 1. dn plus 1. So dn is what? So d1 is an interval. By the way, you may see that F0 is a pair of 2 points. Here I'm drawing for US1. And this is called D2. You take it S1 and you fill it up. Here I can draw to you S2. And similarly, I have a ball called B3. Okay, so this is about disks and spheres. What is interesting about disks and spheres is that Sn plus 1 could be understood as Dn plus 1 together with another Dn plus 1 glued along Sn. So once again, the baby example is that S1 is D1 and D1 glued by S0. D1 is this, another D1 is this, and this is how we glue them. You say this is simple. Similarly, S2 is one disk, another disk, and you glue along the circle. Okay, so from this, we go to understanding of the three-dimensional sphere that we cannot see with our eyes. So it is ball 3, so you understand the ball. Okay, another ball 3, and you glue these two balls along S2. That is a boundary of a ball. So here we have to invoke a bit of your imagination. Now, what is this Z2 group acting here? It takes point on one ball and identifies it with a point on another ball. It is actually given by equation x is going to minus x. And now, what does it mean to take a quotient? It means that we are taking only one. We are taking only one ball. But we are gluing the boundary to itself. And this is exactly S3 over Z2. And this space is also known as RP3. And this is also known as a group of rotation. What is interesting is that this group of rotations has a non-contractible cycles. Actually, if I start here and go all the way here, it is a cycle because these 2 points are identified. However, I cannot shrink it to a point. And actually, this property of the group of rotations led people to a lot of confusions in physics. And this Z2 kind of stands for the question what is a spinor? So probably you heard that elemental particles are spinors, like electron is a spinor.
Andrei,
And you
just
may
a
ask-
moment. I might have missed, did you explain what is the notion of a symmetry group and what is the cyclic group of 2 elements and what is the action of a group in a space
course
like a
not.
sphere?
Of course
No,
not.
okay. So I will
Of
do
course
it.
not.
I will
You
do
see,
it.
yes,
I will
you will do it.
Okay.
You see, I am giving.
Next week. Okay, next week. Fine. Mhm,
So
next week.
that's how we go. I am giving you ideas, okay? So you should think about ideas, and then you should be interested in getting more details. But you will think about, you will spend your time on studying the details if you will hear the ideas, and you would like to see how it works in some detail. I am giving you the ideas that you would see, okay? So understanding of this, Z2 stands for our understanding of what a spinor is. And why spinor has 2 components, up and down. What does it actually mean? You can never
Okay, Andrei,
understand
I will talk of all of this next week, hopefully. Yes,
Totally,
hopefully.
surely. Just hold on.
Okay, good.
see?
Mhm.
You see, I'm doing an appetizer, you see, a trailer. Why? So you heard about this, but probably you don't understand it. So somebody do, somebody don't. But this is because of group of rotations has very particular form. Okay? So just thinking about rotations leads us to kind of a deep and interesting notions. And here we are coming to the very interesting notions of a Lie group. So Lie group, it is something that is simultaneously a group and a space. And we are here. So how did we came here? We came here because we were trying to understand what is the meaning of momentum. And how did we got to this momentum? We were trying to understand what happens with skaters, why they could rotate that fast. And later, what happened with the gyroscope in these experiments? Okay. So just thinking about it led us to a lot of deep questions. And this is a time, you see, I'm bringing you a lot of ideas. And let me give you the last idea here. So let me see the time. Okay, I'll be in time. Last idea. We have r to the power 3n variables and a lot of equations. So how can we study such a system? The number of variables go to infinity, and also infinity many equations. However, what is interesting is that the space of solutions is finite dimensional. So there was a deep thing saying that configuration of a solid body in in dimension d. You see, I always try to work in dimension d, because if I can lower the dimension, keeping the phenomena, I would do it for understanding. You see, d is like all cats. D equal to 3 is a tiger. D equals to 2 is my cat. Okay? Is actually RD times the space of rotation. So, if you have a solid body, like a brick, that I drew last time, and you have another brick, then you can go from this configuration to this configuration by doing translation and rotation. And this is Charles' theorem. Okay? It's a theorem. In dimension D. In the language of mathematics, we say that configuration space of solid bodies is a torsor over a group of isometries. So here we have a new name called torsor. New notion, you see? If you want to understand something, you have to develop the language. So, in simple words, torsor is the following. Suppose you have a group G. Suppose you have a space Y. And there is a notion of group G on space Y, such that for all pairs,
A notion notion of action, Andrei, you didn't say the word action, the notion of action.
So I assumed, okay, I'm not giving mathematical definition. I told that symmetry form a group. And how people understand symmetry is that something acting on something. You see, everybody understands that the action means that you are taking a point to another point. But you see, for all pairs of y, you have a single G for a pair. So typical example of a torsor is the following. Consider a plane. For 2 points on the plane, you may form a vector. So vectors form a group because you may add them. But for each pair of points, you have a single vector. That's why plane is a torsion over a group of translations. You see, this is easy. So you should know it from high school, the notion of torsion. So if people fail to give it to you, okay, it's first of all your problem, and then it's their problem that they don't know this important thing. But that's what happened. And now, what would happen if I replace a group of translations by group of isometry? So isometry is a transformation of space Rd to itself that preserves length. And we know why do we need it? Because we want to preserve length. Otherwise, it's not a configuration space of the solid body. So the space of configuration is a torsion. So that's why it's very important to study the group of isometries and specifically the group of rotations. And that's how we are coming to this problem. That without understanding this, you would never understand neither how gyroscope is moving. And instead of understanding, you will do these experiments that I showed you. You will also not understand fundamental physics, because fundamental physics is based on the notion of the group. Okay? And we will teach you all these notions in the mathematical part of our course. So you may call it physics, you may call it mathematics. In Russia, we do not make a difference. We call it science. Okay? I know people try to exclude mathematics from science, but mathematics is not something very abstract. Just you imagine axioms, you are playing with it. You see, all axioms, all structures, from my point of view, could come out naturally from the problems you are studying in the world around us. Okay? So now it's time for questions. So while I'm waiting for questions, I go to show you some pictures. And these pictures would be pictures people who invented all this. In particular, let me show to you this man. So this is a Sophus Lee. So why I'm showing you all these people? I want you to appreciate how wise they are. You can look in his eyes, and you will see that he would not tell you nonsense. So he actually invented groups that are simultaneously spaces. Let me show you a person who invited the notion of a group. Okay. Galois. He invented the notion of a group. His group was not continuous. His group was discrete. Maxime, do you see Galois on the screen?
I do see Galois. I have minor disagreements, though.
Okay.
My first remark would be the following: that there is a remark in a book by Felix Klein, which I really liked, which says the following: that he and Sophus Lee had a gentleman's agreement that Felix Klein will be studying the finite groups of symmetries, like, say, we can rotate icosahedron 60 times. There are 60 different rotations of icosahedron, yes? And Sophus Lee will be studying continuous groups or topological groups, like we can rotate sphere or a circle in an infinite number of ways. So the notion of a topological group was not invented, divided the field into two topics so that they do not come into any conflict of priorities, which is sort of ourselves, that I, Felix, continuous groups, topological groups. Yeah, and the second remark, I do not know the theory, the history here so well. Galois was a genius mathematician, a very good mathematician, but he was not the person who invented the notion of the group of symmetries, in particular the symmetries of the equation, of the polynomial equations was studied by Lagrange before Galois, and Galois wrote to Lagrange. So the notion of the symmetries on a finite set says so that the set of 3 elements has a group of 6 symmetries. They were studied before, for example,
Kim, your sound is not good. I'm sorry.
Lagrange before Galois, and we know the history well enough.
Maxime, your sound is not good. I'm sorry.
I'm sorry. So hopefully next week it will be much better.
Okay, so now you may also see the Kepler. So why I put Kepler here? Not only because he was before Newton and Newton proved what he did. It is also because, you see, here you can see his writing. And his writing, it's about the motion of the planet around the star. So when it comes closer to the star, its angular speed grows. It is the same phenomena. However, I consider what skaters do much more effective, okay? Then just this small correction because of this elliptic motion. Now, I want to show you another picture. You may think how this is related to mathematics, okay? So whom do you see on this picture? You see somebody who is called the Cardinal Richelieu, who was the actual ruler of France at some period. And there was a war with England against rebellion. And what you can see in this picture, you can see this great Richelieu and some general and some priests, because it was a religious war. And Richelieu was also the leader of Catholic Church in France. So do you know where you can see mathematician? You cannot see mathematician. Mathematician was not that how to say, honored to be placed on this picture. But you see what this mathematician created. You see this wooden construction. And all this wooden construction stopped English fleet to help rebels. Okay? And then why I call this person mathematician? What did he actually, who was this mathematician? I'm not sure that you know the name of this mathematician. But I'll show you this mathematician. So do you see this guy? So I don't want this. I want this. So the name of this mathematician, and he was not only a mathematician, he was also an engineer, you see? His name was Desargues. So not only he can construct something real that helped France to get victory over the rebels and over England, he also invented projective spaces that I was talking about. That the group of rotation is a projective space. And these projective spaces were invented by this man called Desargues. Now, I want you to show you another person. Okay, could you see this person? I hope you can. So it is Monsieur Charles who proved that you can put one solid body into another solid body always by rotations and translation. Okay, good, you know it. He looks a bit crazy, but he's not crazy. And let me show you another person. And this person was this. Hermann Grassmann. He actually made a lot. In particular, he realized that you should study multidimensional spaces. Now it's pretty obvious that we may study multidimensional spaces. However, he made a lot of contribution that we are using now in physics, in mathematical physics. So he actually discovered supergeometry and many other things. Okay. So I think I showed you all pictures. Now we are coming to the equation section. So I have an equation. What is a torsor again? Suppose you have a group. And suppose you have a space. And suppose a group G is acting on Y. So this space doesn't need to be continuous, and group doesn't need to be continuous. Then Y is a torsor over G if for any two elements Y1 and Y2 that belongs to Y, there is unique G such that G Y1 equals Y2. So, example, the simplest group G is S2. It contains of two elements, 1 and transposition. And let me consider as Y space considered from two different points. One I will call white, another I'll call black. So one acts like this. It takes white to white. Okay, if it's white, I should draw it as white. White to white, black to black. And second, there is a transposition. It takes white to black and black to white. So this space consists of 2 points. Y is a torsor over G. So group G is given by the only relation. Okay, 1 times sigma is sigma, it's clear. 1 by 1 is 1. Sigma, composition with sigma is 1. So this is this group S2. It has this multiplication table. And Y is a torsor over G. For each 2 points, there is an only element that goes between them. If I take a pair WW, this element is 1. If I take a pair black, this element is 1. If I take a pair WB, it is sigma. If I take a pair BW, this element is sigma. From this, it means that as a set, if Y is a torsor over G, then as a set, Y is isomorphic to G. However, this isomorphism is not canonical. Like, as a set, I have 1 sigma, and I can map it to say black and white. 1 goes to black, sigma is going to white. Or I can take another isomorphism. Even these 2 isomorphisms are equivalent. Or they are not equivalent, but they are different. So that's why the notion of torsor is kind of different from the notion of a group. However, they are related. It's very important to know that sometimes what you are talking about is a torsor. So it is the simplest example. Second example that I like is a plane. You take 2 points on the plane and you form a vector. And you can add vector. You cannot add points. So plane is a torsor over a vector space. Considered as a billion group. Now, another example. Consider the group SU2. This is a group of rotation. It is parameterized by an angle of rotation that goes from 0 to 2 pi. So altogether, it's S1. However, these rotations are act on S1. You can take a point and you can rotate. So S1 is a torsor over rotation of a plane. So people call it SO2. And this kind of explains the name torsor. You turn. That's why it was called torsor. It is because S1 is a torsor over the group of rotations. Okay. Any other questions?
Yes. Would you explain a little bit more about the correspondence between conserved quantities in physics and symmetries?
So it is okay. So it depends if you know quantum mechanics or not. But okay, I will explain it in Hamiltonian language of classical mechanics. That I will explain later on. But you want to know the answer right now. So I'll tell it to you right now. So I described configuration space. It's called Y. Actually, the discovery of Hamilton says that you need to go from configuration space to so-called cotangent space. So in the lecture of Maxim's, you would see what this space is. In particular, you see, to give you the idea, if space Y is something like RK with coordinates yi, then this space has coordinates yi. Okay. Physicists prefer to put index of coordinates up, pi. They put it down to show that it is a coordinate in the dual space. And then it turns out that the equations of motions of D and M could be written in the following way. The evolution of functions, okay, I call these variables Q. Okay, I call these variables phi. So these are conventional, it's a conventional notion. With respect to T, is actually so-called Poisson bracket of function phi A and Hamiltonian phi A. So I need to tell you what is this Poisson bracket. It is df over dy, dh over d pi I minus df over d pi I dh over dy. Okay, then in this language, this is equation of dynamics given by h of phi. And f is conserved if bracket f and h equals to 0. However, I can read the same equation in the opposite way. F is a symmetry if FH, if HF equals to 0. So here the symmetry is surprisingly given by a function. Okay, so if you have mechanical system, symmetry are not just vector field, as you may think. They are very special vector fields generated by functions. So this means that f is a symmetry. This means that f is a conserved quantity. It is the same condition with two different interpretations. So in order to understand why this is actually the meaning of the symmetry, you have to understand why we should go to this phase space. It's called phase space. It's one thing. Then why equations of motion could have the following form. What are these p's after all? P variables. You see, you need to know a lot about general language. But if you know it, if you study proper language, then Noether theorem is just two interpretations of the equation that the Poissonian bracket between f and h equals to 0. And if you want to go even deeper, then you may say that this equation actually follows from Dirac description of quantum mechanics in classical limit. So this is the fundamental thing. In the classical limit, when h Planck is going to 0, we find this. And then this is a proper, here if we exclude P, we go to DNF. So this is a deep level of understanding. Here we make first simplification. Here we have another simplification. So the wisdom goes opposite way. The wisdom is to go from this here, and this is done by Hamilton, and to go from this here, Dirac. You see, if you use wisdom, then properties of DNM are pretty obvious. Okay.
Okay. Yeah, I think your final remark is very interesting. Wisdom, yes.
So the wiser you are, the simpler is derivation. However, when you become wiser, you can apply it not only to the problem that you are studying, you can apply it to many other things. So you may apply it, you see, not only to understand Noether theorem, okay? You may apply it, you see, to understand the quantum structure of the universe.
Yeah, I have another question that I think I can understand why algebraic geometry is important in understanding understanding physics. But I don't quite get why differential geometry is important. I mean, how does differential geometry help to understand physics?
I started to explain this. You see, the time is linear and the space of concept is not linear. So I have to go all the way around it. Differential geometry is important because we have infinitely many, not infinitely. You have a lot of variables, okay? And you have a lot of constraints. And finally, what you get out of it is something finite dimensional. So I showed you some example with the solid body. In the solid body, you have a lot of coordinates restricted, but you are left with a space that's called configurational space. So it means that we need to find out a way to work with some spaces that we never thought about, like configuration spaces. They are not subspaces of R3. They are subspaces of R3n. So they could be almost everything. And the way to work with them, is to study the most general continuous space. Try to understand how to work with it. We cannot work with them in coordinates. You see, in coordinates, in natural coordinates, in coordinates of the particle, we have billion of coordinates with billion of equations. So how to work with it? And there are two ways how to work with it. Algebraic way, just by looking at ideals, and then instead of looking at ideals, you start working at the coset rings. Okay? So when ideal is big, the coset ring could be finite in some sense, but it would not be a free ring, it would be something else. So this is one way to treat it. Another way to treat it is to say that in many cases, what you get after imposing these constraints locally looks like a disk. So let us work out what happens on the disk and then glue these disks together.
Okay, I see.
Okay, Professor, a short question. I think the last formula, the DNM, this formula, I think is similar to gradient flow. Are they related? Gradient flow.
In the gradient flow, it is so in the gradient flow, it is the velocity that you study.
Yes.
But here it's an acceleration. To make it a gradient flow, it's better to introduce new variables. And new variables are exactly what I started to write. Let us introduce new notion, new concept. MIDRIT, let us call it PI. Then DNS equation of motions would look like, this is an equation of motion. Let me rewrite it in this way. PI is MI DRI over dt. And then Sorry, I want to write it in this way. And also dpi over dt is the gradient with respect to Ri of u. Now this looks like gradient flow.
Okay.
However, it's not a general gradient flow. It is very special flow. Of course, it's a flow, okay? But it is a flow of the special type. So when I write here I over mi, I could also write it in the very instructive way, pi squared d over d pi pi. You see, to make things symmetric. And here is
Okay.
important.
Here in the formula, the u, the independent variable of u is r. Is it right? Ri or things like that.
So
Variable.
when I do the first order formalism, then phi is actually a pair of pi and ri. So this is called the phase coordinate. R is called configuration, so it is called phase space coordinate.
Oh, phase space. Yeah.
And then you may see, look, it looks pretty much like gradient flow. Almost as a gradient flow, because it is d phi over dt d phi I is some strange thing, some constant matrix, and here you have dh over d phi I. And this matrix somehow takes coordinates into momentum. So actually the proper formula is like this. When omega ij, you see, in terms of phi, it is this.
Okay.
Such equation looks similar to gradient flow. So the difference is that here we have a symmetric matrix. And here we have anti-symmetric. And it means that vector fields are kind of different. So for symmetric matrix, we know that gradient flow typically go like this. However, for anti-symmetric matrix, we typically have something like this. So these are called Hamiltonian flow, and this is called gradient flow.
Okay. As the picture you draw just now, for the gradient flow, it means for this kind of differential equation, the solution blows up or things like that.
Okay, so for gradient flow, I can draw you the picture. Suppose we have a sphere. You flow out of this place, you go here. So this is how it goes for gradient flow. You can grow and you can go down. And the condition of gradient flow is that d over dt of the gradient function is positive or negative, depends how you call it. Depends on the choice of the sign. So you go from upside down. However, for antisymmetric matrix, what typically happens is that you rotate. And when you have this flow with antisymmetric matrix, the important condition is that this flow preserves symplectic structure. So gradient flow is not preserving anything. It's only monotone.
Oh,
Flows
yeah,
that
monotone. Okay.
yes, flows that I'm writing have another property. They're preserving symplectic structure.
Okay, okay, understand. Yeah, you means if we use the sometimes the solution go decrease and sometimes solution increase depends on the sign of the in front of the gradient flow.
So if metric is positive, you can prove that that function f decreases along the flow.
Okay.
It comes from the positivity of the metric, but it is the only thing that you can say about it.
Okay, thank you.
So let me say the following. So people who want to leave may leave. It's normal because we are like 48 minutes behind the schedule. People who want to ask questions may stay and ask questions. So that's how we do it in Russia. When you have a seminar is going until the last person who wants to ask question is satisfied. So you may ask any question. But I'm not going to give new material. I mean, new material can appear only in my responses to questions. So I see there are no more questions. So thank you for attending. See you tomorrow. We will continue. Goodbye.
Thank you.